We prioritize languages like Python and JavaScript because they offer developer velocity and memory safety. But at the lowest level, microprocessors execute contiguous streams of binary machine code, acting upon raw memory addresses and physical silicon registers. Physical CPUs cannot inherently process abstractions like dynamic types, closure environments, or polymorphic objects. They are limited to the rigorous constraints of the hardware's specific instruction set architecture. To bridge this divide, we use sophisticated virtual machines and runtimes, such as CPython and Google's V8, predominantly engineered in C and C++. These runtimes act as the translation layer between high-level logic and physical hardware. This creates a semantic divide known as the abstraction gap, the space where human-readable code must be systematically stripped of its convenience to become machine executable. To understand the performance of our code, we must trace its lifecycle down the entire stack, from source text and ASTC structs through virtual machine paradigms and finally to the hardware-level system calls in the kernel. The journey begins with the raw byte stream of a source file. The runtime's lexer scans the stream and uses internal state machines to group characters into discrete, categorized tokens, identifiers, keywords, and operational symbols. CPython has a unique structural requirement here. It must track physical line indentation to emit synthesized indent and dedent tokens. This dictates scoping to the parser, a functional necessity that replaces the braces used in languages like JavaScript. Once tokenized, the stream is fed into a parser, such as CPython's PEG parser, which transforms the linear list of tokens into a hierarchical abstract syntax tree, or AST. In the runtime, AST modes are physical, tightly packed C structs defined by the abstract syntax description language. They link into a directed acyclic graph. These structs use unions and enum flags to store precise metadata, allowing the runtime to generate accurate stack traces. This AST serves as the rigid memory foundation required to cross the first abstraction gap before the compiler can generate executable bytecode. The runtime traverses the AST to emit bytecode, which executes on a simulated virtual CPU. This internal engine manages the computational state and dictates how the program actually runs. Virtual machines fall into two architectures: stack machines like CPython and register machines like V8's Ignition. CPython's stack machine pushes values onto an evaluation stack and pops them for calculations. This keeps bytecode small, but requires more operations to complete a task. Historically, this happened in a massive C switch statement, but that caused frequent hardware branch prediction failures. Modern CPython uses computed gotos, replicating dispatch logic across multiple branch sites to help the CPU's branch predictor learn sequential patterns. V8 Ignition uses a register machine architecture. It specifies virtual registers and a central accumulator. This mirrors physical hardware, significantly reducing the dispatch instructions the engine processes. These two designs represent a fundamental trade-off. CPython prioritizes compact bytecode size, while V8's register model prioritizes higher interpreter throughput by reducing dispatch overhead. Even the most efficient interpreter faces a performance ceiling due to the continuous overhead of bytecode dispatch. To reach near-native speeds, modern runtimes utilize just-in-time, or JIT, compilation. V8's multi-tiered pipeline starts with Ignition collecting type feedback. Hot functions promote to sparkplug, then turbofan for optimized machine code. If data types change at runtime, turbofan triggers a de-optimization, discarding the code and falling back to Ignition. CPython avoids this heavyweight AST to machine code pipeline because of the massive memory overhead and the requirement to bundle compiler toolchains like LLVM.
Instead, CPython 3.13 uses a Tier 2 copy and patch JIT. It uses precompiled binary machine code stencils with holes left for runtime variables. When a loop becomes hot, the JIT copies these stencils into executable memory and patches the holes with specific runtime values, eliminating bytecode dispatch with minimal memory overhead. By utilizing localized dynamic compilation strategies, modern runtimes can bypass the interpreter entirely for the most intensive parts of a program. Performance isn't just about execution speed, it's about memory. Requiring a separate kernel call for every dynamic object's allocation would create a massive system bottleneck. CPython manages this through the ob-malloc subsystem, a specialized allocator designed specifically to handle the millions of tiny objects created during execution. Memory is managed in a three-tiered hierarchy. Raw memory is carved from 256 kilobyte arenas into 4 kilobyte pools. Each pool is dedicated to a specific size class, which is then divided into individual blocks. This allows CPython to satisfy memory requests almost instantaneously from pre-warmed blocks. V8 handles the same problem at the hardware level, using a technique called pointer tagging to represent values without always traversing the heap. If the last bit is 0, it's a small integer, processed in registers. If 1, it points to the heap. V8 also uses hidden classes, tracking structure evolution to bypass slow lookups and fetch properties from pre-calculated offsets. These localized allocation schemas and hardware-level bit masking techniques allow runtimes to maintain the illusion of dynamic flexibility on top of a rigid hardware foundation. User mode applications cannot directly access physical hardware. When code needs to write to a file or a network socket, it must trigger a synchronous hardware exception to escalate execution to ring 0, where the operating system kernel handles the system call. Bridging the virtual machine to these low-level C functions requires the Foreign Function Interface, or FFI, which defines the strict calling conventions for passing data across the gap. CPython uses meth-fastcall, passing a raw native C array of pointers to avoid temporary heap allocations entirely. V8's Fast API embeds C++ call instructions directly into JIT-compiled machine code, passing arguments as native hardware types through registers to bypass object wrapping. To maintain safety, these fast calls are strictly limited: no allocating on the heap, no invoking the garbage collector, and no calling back into JavaScript. Reaching the bare metal efficiently requires these specialized pathways designed to eliminate the last-mile latency between virtual logic and physical hardware. We can now trace the execution path in reverse, from the kernel system calls, back through the FFI and JIT-compiled machine code, through the register and stack-based virtual machines, and finally back to the original source text. This entire journey shows that the expressive, dynamic nature of our code is built upon a foundation of C and C++ systems architecture that translates human logic into the binary format required by the machine. A single line of code is executed through a complex interaction of AST C-structs, register-based virtual machines, advanced pointer tagging, and memory arenas. These architectural details explain specific performance outcomes. We can see why maintaining type stability prevents de-optimization traps in V8, and why modern FFI conventions like fastcall improve throughput by eliminating temporary heap objects. The physical reality of the runtime stack defines the limits of high-level execution. By tracing the logic down to the silicon, we can see exactly how the virtual machine manages the semantic divide between our code and the physical processor.